going to talk about threshold circuits.
Hey, thanks for coming. Thanks to organizers for inviting me. The organizers asked me to speak about my work with others on threshold circuit lower bounds from a couple of years ago. So this is not brand new work, but there are several interesting tools that I think are worth focusing on and bringing up again for the purpose of this semester. So I'll warn you, this is 2 one-hour talks compressed into 30 minutes. So we'll see how it goes. I think it will fit. So yeah, as I said, this talk is kind of a zombie merger of 2 previous talks. Okay, so warning. So the first talk, or part, is on superlinear gate and superquadratic wire lower bounds against depth 3 TC0 for computing some explicit functions. So this is majority of majorities of majorities. This is work with Daniel Kane that appeared in Stock 2016. It uses random restrictions. So it uses a very kind of classical way of thinking about lower bounds in terms of randomly restricting the inputs. Okay. So in that part, the slides have a black background. In the second half of the talk, we will switch backgrounds and we'll prove some somewhat larger gate lower bounds against threshold of threshold. So depth 2, but arbitrary weights as opposed to depth 3, which is TC0, which is majority of majorities, for a not so explicit function. So it's computable in time to the order n with an NP oracle. But it does use totally different techniques. It gets some satisfiability algorithms in order to prove the lower bounds. It uses probabilistic polynomials in a crucial way. And I do want to point out that Suru Tamaki showed similar but slightly weaker results than what I will say, also using probabilistic polynomials with a different construction. And at the end, I'll talk about open problems. So because of this switch between black and white background, I feel obligated to tell you that it is not known to the state of California that watching this talk is helpful for your vision. Okay, I believe I have legally covered myself. Very good, let's go. So I want to start by just recalling what is a linear threshold function. It's sort of the key object of this talk. So it's a Boolean function taking in inputs, giving one output. And so it's implemented by real valued weights, one for each of the inputs, and a threshold weight t. And so that for all Boolean inputs, this function outputs 1 if and only if the sum of overall I of wi x of I is at least t. Okay, some linear form is at least a threshold value. Okay, and what's powerful here will be the weights. Okay, it sort of leads to the current barrier in lower bounds. So just think of it as some kind of thing that takes in bits and outputs a bit and is checking this condition in the middle. Okay, so these things have a very long history, so-called perceptrons, studied many decades ago. In this talk, we'll be talking about depth 3 and depth 2 circuits, where you get to, so this is called multilayer perceptron with one hidden layer, but for the rest of us, it's a linear threshold whose inputs are the outputs of other linear thresholds. Okay, so this talk, the usual notation, I guess, nowadays is threshold of threshold, is how you say that. Okay, and it looks something like this. Okay, there's a single output gate giving the Boolean value, and there it's taking inputs from some middle gates. Okay, and this is the so-called hidden layer, these middle gates. This is computing some Boolean function. So just a very short history of things here. So every function, so it's computable by threshold of threshold, but it could have exponentially many gates or wires. It's not hard to see this. So one question is, which functions, so thought of as infinite families of Boolean functions, have a threshold of threshold family with polynomial mini-gates? Okay, which do not? Okay, so this question is largely unanswered, really. Like if you think about explicit functions in P or an NP, we really don't know very much. In fact, the question was open for a linear number of gates, okay, as we'll see. But there has been some progress on this, and this is what Daniel and I were looking at. So In Palazzo, Paturi, and Sachs showed that the parity of n bits needs into the 1.5 wires at least, and this is tied in the average case. You can exhibit something that has order this many wires on average. It was also shown that inner product mod 2 on n-bit vectors needs at least a linear number of gates, okay, by Roy, Chaudhary, Orlitsky, and Su. And if the weights in one layer are restricted to say like -1, 0, or 1, either the top or the bottom, there are exponential lower bounds known. In fact, even very recent work of Arkadev and Nico Mande shows that there are functions in threshold and threshold that cannot be computed by so-called thresholds of majorities. Okay, this was actually an open question. So this is so-called TC0 depth 2 lower bounds. So if the threshold of majority is majority of thresholds, and so on. You saw talks about these things yesterday. Okay, so it was open whether, say, a huge class like E to the NP had threshold of linear number of gates and slightly more than 1.6 wires, something like this, or even majority circuits of similar parameters. And so what we showed was some lower bounds for explicit functions. So first off, there's an A, so that it's computed in polynomial time. In fact, it is in TC0 depth 3 with a linear number of gates, okay? And it has depth 2 thresholds with cubic number of gates. But we can prove a decent polynomial lower bound. So it doesn't have thresholds of in the 1.5 roughly gates, nor within the 2.5 wires by some polylog factor. Okay, so there's still a gap, kind of, what is the threshold complexity of this function. But the main thing is that this is nonlinear and this is superquadratic. It holds even for some sort of average case. See? The next theorem we show, it holds for depth 3, TC0, so majority of threshold, in fact. So we show there's a function that's computable in NC, probably in TC0. I didn't actually check, I guess. But we can show it doesn't have majority of threshold circuits of roughly similar parameters. So we get to kind of throw a majority on top of this function here. Okay. So the first theorem 1 is proved using a function that is used in the Boolean formula lower bounds called Andreev's function, which I'll review. Theorem 2 uses some modified Andreev's function, which sort of applies the error correcting code to one half of the input, which I will not talk about. I just don't have the time. But I will talk a bit about theorem 1. Okay. So just to review Andreev's function. So it uses this thing called a k-bit multiplexer, which takes 2 to the k inputs and along with an extra k-bit string. It uses the k-bit string to index into the longer 2 to the k string, sort of casting this bit string as an integer and then out, like say I, and then outputting x of I. Okay, then Andreev's function on 2 to the k plus 2 to the k bits can be seen as follows. So you are dividing the input. Sorry, this thing stopped working, this pointer. So you divide the input into 2 halves. So you still have your 2 to the k bits as before. Now you have these different groups, k different groups of bits, and each group has 2 to the k divided by k. And all you do is you take the parity of each of the k groups, you get some bit, and then that indexes into this bit string here. Okay. So it's a composition of this multiplexer with parities. Okay, so theorem, so first shown by Andreev to be in the 2.5, there was a lot of improvement, then optimized by Hostad, shows that this thing requires formulas of size about n cubed divided by polylog n. I think Avishai improved sort of this factor. It's still, I mean, there's order in cubed size formulas of this thing, so it's still like a question of finding something better for sort of any explicit function, actually better than n cubed.
So the second example that you mentioned is better by log n. The one where you take error correcting code is harder than Andreev by a log n factor at least.
Okay.
Provable.
So the polylog degree decreased by 1. Okay. Okay. But you don't get to throw a majority on top of it. So our proof of theorem 1 is going to mimic aspects of this basic idea. So I will just say at a very high level how it works. So here's just a reminder of Andreev's function. So as usual, if you use random restrictions, you define some random process on a Boolean function and output some Boolean function on a smaller number of inputs. That's the way I like to think about it. So you have some process here R, which say randomly chooses all but 100 log n inputs to f and sets all the others uniformly at random. So it picks some at random and set some small subset and it sets all the others uniformly, and then you output this small function. Okay, so it's a very natural kind of way to restrict a function. You want to analyze kind of what happens to the circuit complexity of this G depending on what the function f is. Okay. So the first lemma 1, which I put in quotes because it's kind of a paraphrase of what we prove, but this is very much along the lines of how the formula lower bounds get proved. So first, on a threshold circuit C of S gates, if our f were coming from such a circuit, then we can say that this random process outputs a G. So the expected minimum number of gates in a threshold of this G is strictly less than S times about 1 over square root of n. Okay, so we went from S gates to 1 over square root of n, okay, in this G. Now, we set a lot of inputs, okay, so this is what we can do. So it's some sort of random restriction for threshold functions in general, this kind of lemma, okay. So the process is expected to output things with sort of somewhat low circuit complexity. And then we want to offset that with a lemma 2, which says that in fact with high probability the thing being output is going to need at least n over pi log n gate thresholds. Okay. So here's like some upper bound on the complexity, and here's a lower bound, and we just want to rearrange the inequalities. Okay. So just to say a bit about this lemma 2, a little bit more. The idea is that, well, if you take a completely random function, you can show that it will need very high threshold circuits by counting arguments. And then the idea is if I'm applying this to this Andreev function, then each of these parities is over a large group, okay? And the idea is that even if I'm setting like a ton of inputs, I want to say that with high probability, for all of these groups, there's something in there that's left unset. Okay? If I can show that, then setting almost all these to random, this thing is basically implementing the truth table of some random function sitting in here. Right? If I leave each of these like unset, then I can still implement some hard function, some hard random function on k inputs. Okay, where k is log n here. So that's roughly speaking why you would get this lemma 2. And so combining 1 and 2, just sort of putting them together, you can show that if a circuit computes this A, then the size must be at least in the 1.5 divided by pi log n. So it's just sort of taking this and putting them together. Okay. So this is the theorem you get.
Right.
Yes?
Do you know if any such circuit can be computed by small formulas, as in you can get it more in a backwards question?
Like any threshold?
Yeah.
I mean, I don't know a good formula upper bound for a threshold, with arbitrary weights. Yeah, it's a good question, actually, just in itself. What is the formula complexity of that kind of thing? Yeah.
In which size?
Like less than n cubed?
Sorry, even just a threshold, a single threshold. I mean, sure, it's a polynomial, but how big does a polynomial need to be? Any naive thing I can think of is more almost like into the 4 or something. But, okay. But here I am, like on the fly. I don't know. Okay. So let me say a little bit more about this lemma 1, this random restriction thing. Okay. It follows from general random restriction lemma. Here's a weak form of what we state. What we state is actually far more general. But this is something to at least give you an idea. So let f be LTF on n variables, and let k be something much smaller than n. Okay, so if we randomly choose all but k inputs to f and assign all the other inputs randomly, okay, this process, let's say, outputs some g on k variables. the probability that g is a constant function on these remaining k variables is actually somewhat high. It's at least 1 minus order k divided by the square root of it. Okay? So this is like kind of the key to thinking about this. And so then having the probability that some gate is a constant function, if it's a constant, you could just remove it in the minimum circuit. Okay? So every time something is a constant, you could have just made it smaller. So then the idea is that, okay, if you set k to be about 100 log n and you're doing this random assignment on things, the expected number of non-constant gates on this bottom layer is actually going to be, say, this probability, so 1 minus this thing, okay, times s, the total number of gates. Because this is the probability that something does not become constant. Okay, so the expected number of things left over that are not constant is that. Okay. All right, so far so good. That's 15 minutes used up. All right. So that's part one. All right, so let's take a moment to adjust our eyes. Okay. I'm just going to, some things just to like, this is not math. Okay, so that, I don't know. Like I think if I were reading this talk, it would hurt my eyes. So okay. Anyway, good. All right, now we can proceed. So now the second part, the talk is about probabilistic polynomials for functions. Okay, again, we're looking at Boolean functions, but we can also think about polynomials over some domain, which is either a finite field or say the reals in the following. So then we say the distribution on degree d polynomials, on say d to the n to the d, is some probabilistic polynomial for the function f with error at most epsilon if for all inputs to the Boolean function, the probability that when I draw a random polynomial and it agrees with the function on that is greater than 1 minus epsilon. So think of this as just a worst case randomized algorithm where your algorithmic model is degree d polynomials. So in order to compute on something, you draw a random polynomial and then with high probability, if epsilon is small, it's giving you the right answer for that function. Okay? So people study what is the kind of optimal error or degree trade-off for these kinds of things. And in some cases, you can do really well. So a famous example of Rozborov is that the OR function over the field of two elements has log 1 over epsilon degree probabilistic polynomials with error epsilon. Okay, so just to review that, so you pick some random subset of the variable indices, and you pick a polynomial just taking a random sum, modulo 2 of those. Okay, so definitely this thing is 0 when you get all zeros. So great error then, error 0, but it's odd with probability a half otherwise. Okay, so this gives you already a degree 1 polynomial with error 1/2. Error 1/2 is maybe not so good, so you can amplify to error epsilon with degree only order log 1 over epsilon by taking different uniform random copies of this thing and composing them like so. Okay. Just sort of a review of probabilistic polynomials and how they work. So in this work with Josh Allman and Timothy Chan, we gave some interesting probabilistic polynomials related to threshold functions, which we use to prove lower bounds, and in fact, do a lot of interesting algorithmic work as well. So first we gave probabilistic polynomials for symmetric functions that don't use much randomness. So in particular, every symmetric function, Boolean symmetric function on d inputs, has a probabilistic polynomial degree about square root of d log s and error 1 over s. So s is just some integer parameter using a small number of random bits. So polylog d s random bits. Okay, so just to clarify, so it was known the year before that you could in fact get something with say omega d random bits. And this matches the old degree lower bound of Rozborov and Smolinski, which was known for many, many years that it is square root of d log s, for example, for the majority function. Okay, this is, it sort of follows from these canonical lower bounds for AC0 with parity that you get that. And it was open for a very long time if that was actually optimal. So we also give a low degree polynomial threshold function for ORs of majority. So polynomial threshold function, you can just think of this as a threshold of ands if you're working over 0, 1, or a threshold of XORs if your polynomial is over -1, 1. And so essentially what we get is a PTF of smallish degree, just as before, so that for all Boolean inputs, so you take some parameter k, it could just be anything between 0 and 2. If the number of ones in that thing is less than k, the polynomial stays bounded. If it's ever gets at least k or more, it blows up to like some s. Okay? So given this kind of thing, you can just take like a sum of s copies of such a thing and implement an OR function of this. So this thing is kind of implementing a majority, in fact, a threshold for k for any k. Taking a sum of them, you can get an OR of it. Interestingly, we looked at probabilistic PTFs. So you have probabilistic polynomials. You could have probabilistic polynomial threshold functions. We have a distribution of polynomial threshold functions trying to compute something. And from the point of view of lower bounds, it's not totally clear what this means, but from the point of view of algorithms, it's very interesting if you can get something better. So we in fact get something which sort of breaks this square root of d degree and gets a cube root of d degree with totally similar properties. Okay, but it's a distribution of things that are computing this function. So these two theorems we use purely algorithmically. It's quite possible they could be used for lower bounds in some way. We use them to design fast algorithms for nearest neighbor in the Boolean hypercube, approximate nearest neighbors in the L2 norm, and stuff like that, improving over lots of different results in sort of the log dimensional case. But it's quite possible these things could be used for other stuff. So I'm going to say, so this thing in the red box, this probabilistic polynomial for symmetric functions, this is what we used to get sort of stronger circuit complexity lower bounds, but for like a not so explicit function. Okay, so we applied that particular probabilistic polynomial to get the following applications. So first, for some epsilon greater than 0, for all of them that depend on the depth and modulus and are sufficiently small, we can solve the SAT problem for ACC of thresholds faster than exhaustive search. And there's an asterisk here. And that only applies for circuits that have, say, a subquadratic number of threshold gates at the bottom. But they could have sub-exponential, say, 2 to the n to the order epsilon thresholds here and such gates here. Okay. So, so it definitely gives you a SAT algorithm for a subquadratic threshold of thresholds, but something more general. You could have like a sub-exponential threshold in this middle part. It's not clear what else you might compute with that, but it's interesting to know. So as a corollary, just kind of applying the known connections between SAT algorithms and lower bounds, we get a function in e to the np that doesn't have such circuits. Okay? So recall that with random restrictions, we got into the 1.5 type lower bounds for gates, and here we get sort of up to quadratic lower bounds for the number of gates. But going beyond that seems kind of tricky, mainly because of this square root of the lower bound on the probabilistic degree for symmetric functions that I mentioned in the previous slide. In fact, it holds for the majority function. So another thing that I want to mention, but I'm not sure what to do with, is that there's a SAT algorithm for more complicated circuits, so AC zeros mixed in with thresholds, and randomized faster than exhaustive search, where these things have slightly greater than linear Fanon into the 6/5 Fanon. And this uses this probabilistic PTF. It uses almost, I think, like most of the stuff on the previous slide, like in the different layers to get like these 3 different layers to work. But because it's randomized, we're not quite sure how to de-randomize it. And yeah, it's not totally clear like what lower bound we would get from that anyway. Yeah.
How do you capture ACC in this class? You have ACC. You said ACC.
Yeah, I'll put AC0 there. Sorry. How do you?
It's stronger, so is it?
Oh, yeah, maybe orthogonal, I should say, instead of stronger. Yeah, right. You're right. It's different. Yeah, depth 3. Yeah. Right. Yeah.
So it's a probabilistic algorithm with error. Is the problem?
Yeah. So yeah, it can make some error, but I think it could possibly be de-randomized. Like essentially, what we used with the fact was that this probabilistic polynomial for sim, like up in the first theorem, we used the fact that it can be done with low randomness, and so you can actually just enumerate over the randomness in the circuit itself. Here, I'm not sure how to do that. Yeah, that's the main bottleneck. So yeah, I don't know what corollary to get out of that. Let me say, I would like to say something non-trivial about the white background part. So here's just a picture of what the thing, that's not the non-trivial part so far. So subquadratic things here, sub-exponential things here, sub-exponential things there, just to give you a picture of what the thing is. So how do we get this SAT algorithm? I'll outline at a high level kind of what the steps are. Okay, so we start over here with so I set alpha to be some parameter for this size versus into the 2 minus epsilon for like this size. It's a sequence of different reductions, and the probabilistic polynomial comes up sort of where in the middle. So the first thing is, at this point, kind of standard to do with a SAT algorithm of this kind. You reduce it to the evaluation problem over all possible inputs. So you fix some into the alpha inputs for the thing. You take the OR of all possible assignments to those. Okay, that gives you again an ACC 0 such circuit with an OR on top. But it has fewer inputs. Each of these thresholds here still have fan in into the 2 minus epsilon. But of course, like these thresholds, like they're now in like sort of different copies for all these different 2 to the the alpha copies we had. Okay, so then there's a step where we use these probabilistic polynomials for a majority. So I said there's these de-randomized probabilistic polynomials for symmetric functions. And the key point is that so we apply it to these here. The key point is that each of these have subquadratic number of inputs. So whenever I apply my probabilistic polynomial of square root number of inputs degree, that degree becomes sublinear in n. So like n to the 1 minus epsilon over 2 degree, if it had constant error. Now I want more error, so because I want to like do some vote over all the possible things, so that it blows up the error, blows the degree a little bit here. But that's the key point, is that like because I have this square root in my degree, I can handle subquadratic LTFs. So it looks like this. So that over F2, it's just some XOR of ands of like lowish degree. All right. Now this top part is still small size. It was just some OR. Before it was just some OR of stuff, and now I'm taking some majority of that stuff. And this thing here is slightly larger, just because it's getting close to n because of this degree here. Now the idea is you take this part, which is still somewhat small, and replace it with a sim of ands in this sort of Beagle-Tyrrell translation, which is, again, a kind of standard thing to do with ACC 0. Okay, you do that. And then you apply the distributive law, because both of these ands have like low fan-in. So this is actually smallish fan-in. It was polylog in the size of the thing. Now this top sim has sort of small fan-in still. I mean, because the quasi-polynomial that goes up from here only makes this some larger constant. So then you set your alpha to be, say, order epsilon, and you apply these so-called modulus amplifying polynomials to this sim on the XOR to remove the XOR layer. Okay? So you get something like this, sim of n of threshold, and then it turns out that things of this form from some older work that I had in Stock 2014 can be evaluated on all of its possible assignments in sort of quickly using sorting tricks and fast matrix multiply. And so you get this kind of SAT algorithm. So you just check if this circuit is ever outputting 1 on any of its inputs, and if it does, if and only if, say, this one is satisfiable. Okay, so that's the big picture of the thing. All right. So I just wanted to sort of show you exactly where those polynomials get stuck in and like where they're useful. Okay, so open problems. So there's lots of nice open problems here. One is tight upper and lower bounds for Andreev with threshold. So we have some cubic threshold circuits for Andreev. I think you can shave a log factor off that size. But we have only into the 1.5 lower bound, which is the truth. Is there some way to improve the random restriction lemma? Is there a better circuit? I feel like this is something we could answer. Okay. Another question very interesting is whether there are efficient thresholds for inner product mod 2. So a negative answer, so showing that's not true, would separate TC0 depth 3, where inner product mod 2 can be computed, from threshold. Another problem, which Luigi is going to talk about in his talk, is getting better sat algorithms for threshold circuits. So this is the state of the art. This is something I talked about, and this is Chen, Srinivasan, and Santanam. So for superlinear wires, you can get some savings over 2 to the n. That delta depends on the epsilon in some way. Another question is, what is the power limit of probabilistic polynomials representing Boolean functions? So you can think of these as sort of approximate majorities of threshold of XOR circuits. So if they're very powerful, then you could use them along with FFTs and matrix multiply to solve a lot of problems very efficiently, break some of these fine-grained conjectures. If they're limited in some way, then you get some circuit lower bounds for some interesting class. So finally, a question I've been asking many times, but haven't got an answer yet. So 4 years ago, I gave a fast algorithm that can evaluate a large threshold circuit on all possible inputs very quickly. So polynomial amortized time per assignment. So we will output a 2 to the n bit string saying what the value is for this threshold circuit. This should imply a lower bound, right? It should not be possible that for arbitrary circuits of this many gates, you can get such a fast evaluation. In fact, if you could, then things like strong ETH and all that stuff would be false. So this should imply some lower bound. I just don't know how to. Okay, that's all. Thank you.
Questions?
As for the first half, when you said that the random restriction simplifies LTFs, what about PTFs?
PTFs. Oh, Valentin has some work also with Daniel Kane about generalizations of this to PTFs. I mean, so it degrades with a degree, as you would expect in a certain way. But yeah, you can get lower bounds for those as well. Like, say, constant degree PTFs of constant degree PTFs, you can get some superlinear lower bound based on what the degrees of those things were. Some trade-off.
More questions?
So the shrinkage is tight for majorities, right?
Yes. Yeah, the shrinkage itself is tight for the majority function, absolutely.
But then you have other methods. If like the bottom.
Yeah, so instead of looking at whether it goes to a constant, I think we talked about this once before, instead of checking whether it goes to a constant, whether it goes to just some other simple function that you could have gotten rid of for a different reason. And so here we're just checking the probability it's constant, but maybe you could just be like simple. You know, and if it's, in other words, if it's sitting there, there's a way to get rid of it. It could mean several things, yeah.
Let's thank Ryan again.